Okay, well, I would like to share with you some results about water on the moon from LRO LAMP measurements. And I want to thank you for inviting me to share these results with you. And if you have questions as we go along, you can feel free to interrupt me, or we can do them at the end, either way. So let's go ahead. My name is Amanda Hendrix, and by the way, I am a planetary scientist with the Planetary Science Institute, which is based in Tucson, Arizona. But I'm based in Colorado, Boulder, Colorado, because all the scientists who work for Planetary Science Institute live anywhere in the world. Some of them live in Tucson, but most of us live other places. So I live in Boulder, and it's going to snow tonight. Okay. So LRO LAMP is the Lunar Reconnaissance Orbiter Lyman Alpha Mapping Project. And what this is a far UV spectrograph. Here's a picture of it over on the right, showing you kind of the layout of the instrument, if you can see my cursor. And it's on LRO, and so what we're mainly doing is pointing nadir down to the surface throughout the whole nearly polar orbit of LRO. The spectral range of the instrument is about 57 to about 196 nanometers. And as I said, we're sensing ultraviolet light reflected off of the surface mainly. Now, one of the goals of the instrument was to look for water ice, and mainly to look for water ice in the permanently shadowed regions, the PSRs. And so one of the first results about that came from actual detection of something like 1 to 2% water ice in these 3 or 4 big permanently shadowed regions of the South Pole. And the unique thing about LAMP is that even though these craters are in permanent shadow, so that if you look with your eyes, they'll always be dark, the whole idea of the LAMP instrument is that it can use as an illumination source stars that emit in the ultraviolet and interplanetary hydrogen that produces light at 1216 angstroms. And so those sources, or a lot of those sources, are largely in the southern hemisphere. And so they actually can illuminate into these PSRs. And then the light that gets reflected back out comes into the LAMP instrument, and we can measure that light. But that's part of the reason that it takes so long to build up a lot of signal, is because those illumination sources are relatively weak compared to the sun. But it's a really innovative way of doing things, and it works. So on the left here is kind of an initial result of the measurement of water frost in these permanently shadowed regions. And then on the right is another analysis using LAMP data. This was from 2015. And again, this is showing the temperature of the regions versus the amount of ice, or a relationship to the amount of ice. So showing that in the coldest regions of the South Pole is where we tend to see the signature of water ice. And depending on how you model it, whether you say, well, it's pure water ice or it's mixed in with some regolith, this paper gave results of something like 0.1 to 2% water ice by mass. Maybe even up to 10% if there's a mixture. But as I'll talk about, the ultraviolet light that we're sensing is not going very deep into the surface. So we're measuring just the topmost grains. So any water frost that we measure has got to be very superficial. and is probably different actually than any water that is measured by other instruments like radar or even infrared. Those are going to be kind of at different depths into the surface. Okay, so here's how we measure water. This is the strong water absorption edge in the far UV. It's at about 165 nanometers, you can see here. Longward of that, ice is very bright, and as you know, ice is very bright throughout the visible. But shortward of about 165 nanometers, it's very, very dark. And so these results here were made using kind of ratios where they measure the off band, which is very bright, ratioed to the on band. And they say, okay, well, if that's a high ratio, then that's a good indication that there's water present. A couple of things here is that, you know, you may have heard that in infrared measurements where you use the 3 micron water band, for instance, to measure water, you have to deal with thermal emission because you start getting thermal emission from the surface at, you know, around 3 microns. And this can be tricky to try to correct out that thermal signature. And so this is actually an advantage of using the far UV water absorption because there's no thermal emission signature to try to have to deal with. Also, this absorption edge is very strong. It's actually much stronger than the 3 micron water absorption. If you look at the absorption coefficient, the change in absorption coefficient over the short wavelength range here is something like 7 orders of magnitude. So it's a very strong band. But like I was mentioning before, so we can use that strong band to detect very small amounts of water ice, but it does take time because there's not a lot of photons coming out of the sun or any of the illumination sources at these wavelengths. And so we do have to take more time to build up signal. Now, hopefully in the future, we can send other UV instruments to the moon that are even more sensitive than LAMP, and so they require less time to integrate to get data. But as it is for now, it takes a little time to build up signal, but it's still working. Okay, let's see. So now I talked about the water ice measured in the PSRs, but what we're actually also doing, since we're in orbit around the moon, and half the time, you know, we're looking at the day side, half the time we're looking at the night side, we can actually look for water on the surface, even on the day side. And it's hard to actually look for this actual spectral signature on the surface in the day side because it is pretty faint. But what we decided to do was to look for a change in spectral slope. And because this absorption is so strong, it ought to, even if it's present in just small amounts, affect the spectral slope just over this wavelength region here. So what we do is we look at the spectral slopes. So what I mean is that we measure the reflectance spectrum over all of the regions of the moon, every place we look throughout the orbit, and we measure the spectral slope in 3 different wavelength bands, 1, 2, and 3. And if water is present, we should not see any change in spectral slope, say, for instance, with time of day in this band pass number 1 or in band pass number 3, because water ice is pretty flat in both of those. But in number 2, it's such a strong absorption there that if there's a variation in water abundance from place to place or with time of day, we should see that here in band pass number 2. Okay. And what we really wanted to look at was colder regions on the surface and also colder times of day. Do we see a change in the spectral slope here, especially in this band pass number 2? So I'll show you some of the results that we got from this analysis. Oh, but first of all, I need to show you since we're looking at variations with time of day, we have to be very careful about our photometric correction, because time of day, you can imagine, is related to phase angle. And so the angle between where the sun is coming in and the point on the surface that we're measuring, and then where our instrument is pointed. And so we want to correct properly for photometric variations across the surface. And so what we did was, as part of the LAMP team, my colleague Steve Liu went through and figured out far UV photometric corrections for average Mare regions on the moon, and also for average Highlands regions on the moon. And so he figured out kind of an average single scatter albedo. But the most important thing is, for our purposes, an asymmetry parameter that feeds into the phase function that we need to apply, because we want to, like I can't say this strongly enough, that we want to correctly correct for the phase angle, so that we don't mistake any phase angle effects for a time of day effect. So what Steve found is that for both the Mare and the Highlands region, these are the asymmetry parameters that he found that we use in the phase function, phase correction. And so what we did was we kind of took an average for both the Mare and the Highlands regions. We used an asymmetry parameter of minus 0.48, okay, with over the wavelengths that we're interested in working with here to look for water. So we think that that's a good way of correcting for phase angle and not having to be concerned about mixing up phase angle and time of day corrections. Okay. Now, oh, and by the way, here are the actual photometric models that were used at each wavelength to fit to sample reflectance spectra from a Mare region and a Highlands region. So you can see that the model that uses that asymmetry parameter that I used fits these data quite well. Okay. I also wanted to show you that the whole data set that we're using is basically from launch, or from when we arrived at the moon in around October of 2009 through the beginning of October 2016. So a good 7 years of data. And so versus local time on the surface, you can see the number of observations that we had, which is good coverage from, pretty early in the morning all the way until late in the afternoon. And then in terms of coverage of longitude across the surface, across the whole lunar globe versus local time, you can see that this is the kind of coverage that we got. Okay. So again, if water is present on the surface, when we look at these spectral slopes, we expect that it will have the biggest variation versus time of day in this bandpass number 2, which is about 164 to about 173. And if water is present and varying throughout the day or with place on the surface, we should not see an effect in region number 1 or number 3. So that's kind of our test that we wanted to run. So let's look at region number 1. Here it is. It's 160 to 163 nanometer. And again, we took the slope of the reflectance spectrum. And what we did here was we looked at 2 regions. We looked at a mostly Highlands region here in the red box. And then we looked at a mostly Mare region here in the blue box. And so you can see that versus local time, you see that these are all of the points here. It looks actually slightly like a convex shape, but when you put on the error bars and bin things up, it's actually not a statistically significant diurnal variation. It's basically flat versus local time in both of these regions. And so what that means is that you know, at dawn, for instance, or at local noon, the spectral slope is not changing, which we might expect if there were something going on. Now, if there's water present, again, we don't expect it to be changing in this spectral region. So this is kind of good. Let's look at region number 3, 175 to 190. Now here, we look at our Highlands region and our Mare region, and definitely versus time of day, the Highlands slope does not change and the Mare region slope does not change. And again, if water is present on the surface, we do not expect it to change versus time. So again, this is good. But interestingly, what we do see is that the Highlands slope is much higher. It's redder than the Mare region slopes. And why is that? It's because of the actual just shape of the reflectance spectrum that we know is characteristic of these regions. So for instance, if you look at an immature Highlands region or even a mature Highlands region, out here in 175 to 190, you can see that the slopes here are much redder than the Mare regions. Okay, we chose an immature and a mature Mare region, and these slopes are quite blue. They increase towards shorter wavelengths. And this is kind of what we expect for these regions because it's kind of indicative of an opaque and especially probably a more iron-rich composition. Whereas in the mature and immature Highlands regions, they are less blue and slightly redder, and so the slopes are a little bit higher. Again, less iron-rich. Okay. Now, let's go to our region number 2, where we would expect to see a temporal variation, a change in slope versus time of day, if there's water present on the surface. And indeed, that's actually what we see. So for the Highlands region and the Mare region, let's look at the Highlands region, the red. You can see that the slopes, there is some scatter in there, but they stay roughly constant throughout the morning, and then they take a dip around local noon, and then they come back up to the morning values roughly, and stay kind of constant for the rest of the day. We see kind of a similar trend in the Mare regions, but again, if we bin them up and put on error bars and really look and see how statistically significant these spectral variations are with time, we find that really it's only statistically significant in the Highlands region, where there's a big dip that's real. And in the Mare region, there's a dip, but really it's not happening outside of the error bars. So this tells us that the Highlands region, something's really going on. The Mare regions, it's a little harder to say. But this trend is consistent with a behavior like water being present on the surface, and then it's going away. It's being removed by some process at the midday, around noon, and that's actually when we expect the temperatures to be highest. So we can plot these slopes. Now we're just going to look at the Highlands region here, since this is statistically significantly changing. And this is a region that is 30 degrees north to 50 degrees north. Okay, so what we ended up doing was breaking it up into 30 to 40 and 40 to 50 north and showing those slopes versus temperature. So here we use the temperatures that are measured by the diviner instrument on LRO and show these spectral slopes that we measured in the far UV versus temperature. And they're pretty similar. I don't think we can argue that we see a difference with latitude. So I won't go into the two different colors very much here. But again, we see that the slopes stay relatively constant for colder temperatures, and then they drop off quite dramatically at the highest temperatures. Okay. So, but you know, what's interesting is these temperatures are much higher than we would expect water to be stable. So something else is going on besides just the temperature that's allowing the water to be present. And what we find is that this trend is consistent with adsorption of water, or some people call it cryosorption of water, where the water molecules are adsorbed onto the grains, and these are at the very top of the lunar regolith. And then desorption, thermal desorption of the water molecules at the highest temperatures. Okay, so we can use the Arrhenius equation to understand the residency time of the water, and this is related to the temperature and the activation energy. And so if you look at different values of activation energy, say 1 EV up to 1.5 EV, you can calculate what the residency time is expected to be. And here we just plot on here what 1 lunar day is. Now the activation energy is related to how well the grains can actually hang on, or sites on the grains can hang on to a water molecule. It's kind of related to a stickiness, and it also is likely related to how rough and irregular the grains are, and perhaps how much they have been weathered. But you can imagine that the lunar grains, especially these topmost grains that LAMP is measuring, are sitting out there in the vacuum of space and being irradiated constantly, pounded by micrometeoroid bombardment, and they're very rough. And we know already that they're just rough and irregular, but those topmost grains have got to be extremely irregular in shape. And that's going to end up being related to the absorption energy. Or activation energy, I should say. Now, there have been lab measurements done on a Highlands sample from Apollo and also a Mare sample from Apollo. And these people, Poston et al., took these lunar regolith samples and then basically dosed them with water in the lab, and then heated them up and watched the water thermally desorb. And what they find is that for different dosing levels here, that the water mostly comes off at maybe, for this amount, this smaller dose, comes off mostly at around 220 or so Kelvin, but a lot of it hangs on until much higher temperatures. And for an even larger dose, more of it even hangs on till larger, higher temperatures. So, you know, in the lab for these actual Apollo lunar samples, activation energy values as high as something like 1.3 to 1.5 EV have been actually measured. And so we can model our data versus temperature to understand what kind of activation energies we are actually sensing on the moon. And we use this relationship to understand the change in concentration of water with time, where we've got K as the Boltzmann constant, and that's related to the activation energy and temperature. KB is the Boltzmann constant, I should say. And we can do a good job modeling the slopes measured at these two latitudes and what we have to do is use activation energies of about 1.24 and 1.3 EV. So again, consistent with what has been measured in the lab for Apollo samples. But what it means is that these are kind of relatively high activation energies. And so this is why the water is hanging on to those grains until relatively high temperatures. And so what we can do then is to model how much water is present. And so what we did was we modeled the water as being a layer on top of the regolith. Because remember, we're not sensing very deep into the regolith with the FUV. So we just measure it we model it as a layer, overlying the regolith, and we calculate what the optical depth is of that layer, and to match the spectral shape that we measure. So here you can see that if there's no water in this dashed dot line, our model of the lunar spectrum, reflectance spectrum, is just this pretty straight kind of blue slope, like what I showed you in the actual data. If you add in a little bit of water, a 0.25% monolayer on top of that lunar regolith, you get a little bump up here where water, the presence of water changes the slope there and makes it a little brighter at the longer wavelengths. And then if you add in like a half a monolayer, 0.5% of a monolayer, you get a little bit more of a bump in slope and a brighter reflectance at those longer wavelengths. And so what we found from doing these kind of simplistic models here is that the aerial coverage that we need to match the slopes that we see is something like 6 times 10 to the 12 molecules per centimeter squared, which is roughly 0.5% of a monolayer. So very sparse amounts of water, but still, again, detectable by lamp thanks to that strong water absorption feature. Oh, these are, I already mentioned that lamp does not sense very deeply into the regolith. And this is because of the sensing depth that can be characterized by the wavelength that we're sensing divided by 4 pi k, where k is the absorption coefficient. And so we kind of have to estimate what the absorption coefficient is of the materials that we're sensing. And so really, at 190 nanometers, we're probably sensing some tens of nanometers into the regolith, which is really not even the size of a grain. So we're just sensing basically the tops of the grains. Whereas if you think about an instrument like M cubed out at 3 microns, they're measuring hundreds of microns into the grains and into the regolith. So again, we're kind of sensing different things in these two instruments. Okay, so back to our diurnal trends. Let me see how I'm doing on time. Okay, diurnal trends in slope. Again, here's our highlands now in pink and our Mare region in orange. So what we think is happening here is that in the morning over here, there's, you know, a fraction of a monolayer accumulated on the surface. Okay, and it's kind of hanging on at steady state. And what we think is that basically, this is probably the case where all of the sites on the grains are probably filled. So basically the activation sites where there's a, you know, if a water molecule wants to adsorb onto a grain, it's going to adsorb onto one of these sites, and they're probably all filled because we don't see any change there. But then when the temperature gets high enough, the water desorbs and the water molecules are released. And where they go, they hop away. Some of them might escape into the exosphere, but some of them just hop away. And what they're going to do is just move to a locally cold region. An available activation site on another grain that's cool enough for it to be stable. Okay, so what that means is just a nearby grain that's at an earlier or later time in the day. And then for this particular site, then those regolith grains and the activation sites thereon will take on water molecules that are bouncing from elsewhere. So that's the kind of the story that we think is happening. Oh, this is our little cartoon of what we think is happening. Again, we're just sensing water molecules adsorbed onto these activation sites on the top of the grains. And at local noon, when the sun is overhead, these water molecules desorb and bounce away. And maybe there are water molecules at more stable sites, slightly deeper down. Maybe LAMP doesn't sense those, and they might be a little bit more stable. Another aspect to this that relates to the migration story and the bouncing around of water molecules story is that we did these measurements also when the moon was in the magnetotail. So you can imagine that for much of the orbit of the moon, it's out in the solar wind. And we think that the water is largely produced by solar wind protons coming in. And, but the solar wind turns off when the moon is in the magnetotail. And so we wanted to see, well, do we see less water when the moon is in the magnetotail because there's less water being produced? And so we looked at these two sites. This one up here in red, this is a Highlands site at, it's 30 to 60 degrees north. And then we looked at another Highlands site because we wanted to look at similar kinds of terrain at a similar latitude. This is northern latitude and this is southern latitude, but they're about the same distance from the equator, same amount of sun and solar wind. And this, as you know, this region here, more on the near side, is going to be in the magnetotail when, or it's going to be shielded basically from the solar wind more than this site here when the moon is in the magnetotail. So we would expect differences between these two regions because this region here is sometimes in the magnetotail. But what we find is that we did not see a difference. So these two regions basically show the same diurnal variations, whether you look at a big region or cut it in half and look at a smaller part of it. Excuse me. You see basically the same trends. And so what that tells us is that we're not seeing water that is immediately formed by solar wind protons coming in and forming water. What we're seeing is water that exists on the surface already and is probably just migrating around. So I'm going to summarize. These results were published last year, and I've got references on the next page. What we see is a diurnal variation in the Highlands terrains, especially, consistent with a small amount of water, less than 1% monolayer. And this is consistent with cryosorption and desorption of water, with activation energies apparently about 1.3 eV. Now, our results are qualitatively, or maybe even a little bit quantitatively, similar with the M-cubed results from Lee and Millikan. They published their results, though, in parts per million, and we chose not to do that because of that requires a lot of assumptions. But that's why we say qualitatively they're pretty similar. But what this means is that near local noon every day, some 10 to the 12 molecules of water per centimeter squared are released into the lunar exosphere. And this should be detectable. Now, when the LADEE mission was in orbit around the moon, their neutral mass spectrometer could have measured that at that 50-kilometer orbit where they were. But unfortunately, they didn't have the temporal resolution because they kind of average data over much longer periods of time. But ideally, one would want to send a mission to the moon that could measure, this quantity of water molecules at noon, local noon, and see if you see it. It's kind of like almost a fountain of water every day at noon that ought to be there. Now we're also working on refining these results to look more on a global scale. So stay tuned for those results. And we have a new operating mode that we're working with, which increases the signal to noise. So we should be able to improve our results even further. And then I've got references here for your use in case you wanted to work on this more. So I will leave this here though, actually, and say thank you very much.